Hello everyone. Today we will start with the first lesson from this course, Reinforced Concrete Design 2 or Structure Design. This course is the second course for the reinforced concrete. Okay, and this is the first lesson. First lesson is about the one-way slabs. This question is asking to design the one-way slab. First of all, we have three slabs as you see. Each one of them, we will design all of them. S101 and S103 are exactly the same because they are in the corner and also their distances are the same, like 3.4 the width and 7.5 the length. But in the middle, S102 is different because the width is different and also it's in the middle. This is the first point. And the second point, we will check the details that we have here. First of all, we have the concrete type, the steel type, the Q is the live load. Some courses will write them as LL, live load, and some of them only Q. And it equals 2.5 kilonewton per meter square. Plaster is something important for the dead load. I will explain this point in the when we are calculating the design of the dead load, and is equal 0.9 kilonewton per meter square. Then we have the BW over H. This is the dimensions of the beam, 25 centimeter and 50 centimeter. The dimensions of the beams are very important. Also, another thing to mention is these dimensions 3.4, or 3.6 or 3.4 are from the center of the beam to the second center of the beam. This is very important. Okay, we will start designing these slabs. So, how to design them? I prepared a PDF file and we will follow this PDF file. So, as you see here, the first point when we want to design one-way slab is to determine if the slab is one or two-way. Yeah, it's written as one-way and the question is saying design one-way, but also we need to make sure it's one-way. It's one of the steps. So how do we calculate it? We refer to this point as M, and it equals the long length of divided by the short length. If the answer was bigger than 2, then it's one way. If the answer was 2 or less, it's two way. So let's start doing it. Okay, so first point, S101 and S103, we will do them together. As I said, they are the same. So the M equals LL over LS. So the long length is 7.5 and the short length is 3.4. When we calculate it, it will be 7.5 divided by 3.4. It will be 2.21 approximately, and it's bigger than 2, so one way. The second one is 102. M equals LL over LS, and it equals 7.5 over 3.6. We need to calculate for each one of them. So this one will be 3.6 instead of, it will be 2.08, let's say 2.1, and it's bigger than 2, so one way. Both of them are one way. Okay, what does it mean, one way? Okay, something different, something beside the explanation. One way it means, let's read this color. One way it means this is the slab we have. So this is the short and this is the long, right? So the steel that we will design the slab of will be laid like this, in this direction, in the short direction. Yes, we will have steel like this, but this steel is not important, it's secondary. This one is the important one, and it will be laid like this, as I just mentioned. Okay, so this is the first point and we've done it. It's one way, sorry, it's one way and one way. Okay, when we move to the next step is saying find slab's depth. Okay, very important, we need to find what is the depth of the slab, what is the thickness of the slab. So we have this formula. HF, it should be bigger than 80 millimeter, 8 centimeter. The slab shouldn't be less than 8 centimeter, and depending on the code, some codes might say 10, 8, 9, 12, depending on the code. And the other point is the formula that we will use. LSN is the span, or the span of the slab divided by 25 is for the simply supported slab. LSN divided by 30 is for the continuous slab. LSN divided by 12 is for the cantilever. Okay, in this case, okay, these two we will consider them, this one and this one, we will consider them as simply, because okay, they are connected from one side here, like S100 is connected from with S102 only from one side. Some doctors might consider as continuous and some as simply. I will consider it as simply, and this one is also simply supported, but in the middle it will be continuous because it's connected from both sides. Okay, so how to solve this one, this second point? Okay, we will start from S101 and S103 again. So we have the formula HF should be bigger or equal 80 millimeter, or LSN divided by 50 by 25, sorry, by 25. What is the LSN? Another point. Okay, LSN is this is the slab we have, this is the beams surrounding the slab. So here, as I said, from the center of the beam to the center of the beam is 3.4, right? 3.4. LSN is this length only, this is in the middle. So as we had in the question, 25 centimeter is the width of the beam. Here we have 25 centimeters, so in the meters is 0.25 because this is in meters. So 0.25, and here we have 0.25. 0.25. So from the middle here to here, the distance will be half of this, and from the middle here to here, the distance will be half of this. So LSN, this is the LSN, only the space in the middle, or the span, the inside span, the inner span. So to minus from it the half of the 25, 0.25, and half of the 0.25, we will have 1.25. We will be distracted from the LSN. So we will say LSN equals what? Equals 3.4 minus 0.25. As I said again, 0.25 is this one plus this one, because they will be subtracted from the LSN, from the 3.4. In that case, we will get LSN over 25. When we calculate this, it will be 3.4 minus 0.25 over 25. It will be 0.126. 0.126 meter. Centimeter. 0.126 meter. Yeah, it will be in the meter. Okay, this is the first one. When we go to S102, we will do the HF bigger than or equal 80 millimeter, or LSN over 30 in this case, because it's continuous. So LSN also the same. Here we have what is 3.6. So 3.6 minus what? Minus half and half of the beam. So 0.25 again divided by 30. In this case, we will have 3.6 and 30. It will equal to 0.11 or 0.112. 0.112 meter. So in this case, we have this is the depth we will take, and this is the depth we will take. One of them we will consider in our question. Okay, the most important point, both of them are bigger than 80. So this is important. If it was less than 80, so in that case it will be different. We will use the 80. But in this case, both of them are bigger than 80. So what we will do, in this case, we have 126 and 112. Which one we will take? We will take 126, because these slabs are beside each other. So we cannot design them according to these two values. We will design them according to one of them, which is the bigger one. Also, we will take the closest bigger number. So 0.2 HF is equals 0.126, and which is equals to in meters, which is equals to 12.6 centimeter. So we won't consider as 12.6 centimeter, we will use it as 13 centimeter. Don't use these numbers, use 12.5, 13, 13.5, 12, something like this. Also another thing, always take the bigger number, not the smallest number. So don't consider this one as 12.5. 13 is the best option. 13 will be acceptable for this one and for this one. That's why we took the 13. Okay, in this case we've done with the second point. Now we will move to the third point. Okay, in the third point, what do we have? In the third point we have, in this case we need to find the loads. To find the loads, what do we do? First of all, we need to define the dead load. As I mentioned before, the dead load is not given. So what do we do in the dead load? The dead load is considered as the self weight of the slab, which is the HF times the gamma or the lambda of the type of concrete, and HF is the thickness, plus any extra loads that we have in the slab. If you remember, I told you the plastering will be considered in this case. So the plastering will be added here as extra load for the dead load. Extra load for the dead load, yes. And then we will calculate it in this formula. I think all of you know this formula: 1.4 times the live load plus 1.6 times the dead load. Okay, we will start solving this point. So first of all, we need to define the self weight. Self weight equals HF times lambda. Okay, HF equals what? HF equals 13, so we will consider it as meter, 0.13 times lambda or gamma, it's the 25, the type of the concrete. So 25, the compressive strength, this means the compressive strength of the concrete is 25. They might give it to you given in the question, tell you that it's 25. Sometimes it's 30, but in general 25 is the most common value. Okay, 0.13 times 25, it will be 3.25 kilonewton per meter. Look for per meter square. Yeah, per meter square. This is the self weight. So the G will be 3.25 plus what? Plus the plastering. Any extra load that we have, the plastering 0.9 plus 0.9. This will be 4.15 kilonewton per meter square. This is the G, and the Q we have it given from the question, 2.5 kilonewton per meter square. As I mentioned before, it was given here. So then I will use this formula: PD equals 1.4 times Q plus 1.6 times G. Or it was the opposite. Let me check. Yes, I was mistaken here. So it's 1.4 times G plus 1.4 times G plus 1.6 times Q. When we calculate it, 1.4 times 4.15 plus 1.6 times 2.5, it equals 9.81 kilonewton per meter square. Okay, it's per meter square, we need it per meter, so we multiply it by 1 meter, because in the reinforced concrete, when we design the slab, we take 1 meter. We design for 1 meter each. Only we take like a specimen of 1 meter, and we design accordingly. That's why this value we multiply it by 1. So it will be multiplied by 1 PD times 1 meter, and it equals 9.81 kilonewton per meter. This is, in this point, we've done with point 3. We are done with point 3. Now point 4. What do we do for point 4? Okay, for point 4 we calculate the moments. Okay, first of all we have two checks. The first check is to use the method of approximate moment, and the second check is to use the method of appropriate moment, approximate and appropriate moment. Okay, in general, these points are important to do, or these two checks are important to do, but like there are always, like all the times that I experienced these two checks, they succeeded. However, these the first one is telling us the short min the minimum short length and the maximum short length. We will take them and they should equals it should be equal or bigger than 0.8. And the second check is the dead load over the live load over the dead load should be less than or equal to. So let's do it very quickly. Check one. What's the meaning of the first check? As I said, the maximum length. So what do we have here? The short maximum the maximum short length, which is this is the short length. These are the short length. So the maximum one of them is a 3.6. 3.6. This is check one. 3.6 divided by the minimum short length, which is 3.4, because these are the short length and these are the long lengths here. So divided by 3.4. 3.6 divided by 3.4, it equals 1.06. Let's go back to the condition. It should be bigger than or equal 0.8. So it's bigger than or equal 0.8. So succeeded. Check 2. Q over G, right? Q was G over Q or cube over G? Just a second. We have Q over G and should be less than 2. Q is 2.5 over G. G was 4.15. 4.15. So 2.5 divided by 4.15, it's much way less than 2. Less than 2. So also succeeded. This one succeeded. So the two checks passed. Then we will start solving the moments. So as we see here, we use this formula always. Like these are in this graph, we see that the first support, the first span, support, span, support, span, support. These two in the corners are the external supports, and they are considered as negative. PDL square over 24, the PDL square over 24, and this is external span, and this one is external span, and we use PDL square over 11. These are constant, and this one in the middle is called internal span and PDL square over 15, and these two are internal supports. One condition in these two internal supports, the length we use is the we calculate the both of the spans that surrounding the support and divide it by 2. Let's solve this point. Okay, first of all, yes, we have this. Let's draw the graph. Is the best way to solve it, to draw the graph to know where you are. Okay, you can draw it the support to down and the span to up, but I will draw it the opposite because I prefer that way. So this is support, span, support, span, support, and span, and also we have another support. So here, as we say, PDL square, or without square, PDL square over 24 negative, and PDL square over 24. Okay, the second, these two, PDL square over 9, PDL square over 9, negative, negative, and here we have PDL square over 11 and PDL square over 11 over 15 and PDL square over 11. So we have this. What are we going to do now? We will calculate the moments of each one. So this is the first one, and so the first external span and the last external span will be the same. But let's sorry, support. But let's start with the spans. Let's finish the spans first, and then we will do the supports. So span and support. Let's do the spans first. So first span one is 101 and is 103 will be the same. Oh, let's call let's call them M101 and M103. Sorry, M101 and M103. So what do they equal? PDL square over 11. So PDL, the P is PD was, we've done it just here, 9.81. Sorry again, 9.81 times the length. What do we take here? This length, the short length, because we are designing in the short direction, which is 3.4. Okay, times 3.4 square over 11, and it equals 9.81 times 3.4 square over 11 equals 10.31. This is the first moment. The moments are so important, and it's kilonewton times meter. Then we start with M102. M102 equals PD L square over 15. Okay, in this case we have PD is equals 9.81, where is the L equals in this case this span, the mid span, so it's 3.6 square over 15. In this case it will equal to 9.81 times 3.6 square over 15. It will equal 8.4748 kilonewton times meter. This is the other one. So now we've done the moments for the spans. Okay, for the supports, first of all, we have x1, x2, x3, x4. We named them as x. So x1 and x4 equals each other, and they equal minus PD times L square over 24. Okay, and it equals 9.81 times the L will be 3.4 again square over 24 minus, and it will equal 4.72 or 73. 4 minus 4.73 kilonewton times meter. Okay, this one is correct. The last one is the one that we need to change it a little bit because it's in the middle span. So x2 equals x3. These two in the middle are equal each other. So this one, x3 and x2 are equal each other. So it's PDL square over 9 equals minus PDL square over 9, and it equals 9.81 times in this case L will equal what? Because it's in the middle span, so it's in the middle span, or it's in the middle, the support is stuck in the middle between two spans, so it will be the cumulative value of the two spans it's surrounding it divided by 2, so it will be 3.5. So times the 3.5 square divided by 9, it will be 3.5, 13.35 equals 13.35 kilonewton times meter. Okay, after this step we will calculate the decrease of in the moment load. Okay, decrease in the support load, moment in the support, decrease in support or in internal support. Okay, these supports in the middle, this one plus this one, will have a decrease in the moment value of them. So the first one is which is x2 and x3, which is the value of it is 13.35. So we will calculate the new value. Okay, how to calculate the decrease of support in support? We will follow this formula. The VD, we will follow these formulas. So first of all, we will calculate the shear, and after that we will calculate the decrease of the moment, and we will calculate the new moment, which is the old moment minus the decrease of the moment. So how to do that? First of all, we will write the formula VD equals PD times L divided by 2 plus M1 minus M2 divided by L. Okay, M1 is we have now this moment here 13.35 and 4.73. M1 is the biggest one. Always use the biggest one for M1 and the smallest one for M2. And neglect the minus or positive sign. We only need the moment value. So it will equal to PD is 9.81 times L. L while it's stuck in the middle, so we'll calculate the average L, which is 3.4 plus 3.6 divided by 2, which is 3.5. So 3.5 times 3.5 divided by 2 plus M1, which is 13.35, neglecting the minus sign, minus 4.73 divided by 3.5, and it equals to 19.63. This is the VD. Okay, so VD equals 19.63 kilonewton. After that, we will calculate the delta M. Delta M equals to, okay, no need to calculate the VD for both supports. We will find the decrease of the support value for the x2 and x3, but no need, because when we want to repeat this for the other support, for this support, we will have the same values exactly. We'll have the same values exactly, because when we compare it with this one, we'll have exactly the same value, the same 13.35 minus 4.73, so no need to do it again. After that, we will calculate the delta M. Delta M equals D or equals V times A divided by 3. Okay, VD, we already have VD, which is 19.63 times A. A is the thickness of the beam. Thickness of the beam was 0.25 centimeters divided by 3. So 0.25 divided by 3, and it equals the decrease of the moment 1.64. Delta M equals 1.64 kilonewton times meter. So the new moment x2 equals x3 will equal to, the original moment was 13.35 minus 1.64, and the total moment will equal to, the new moment will equal to 11.71 kilonewton times meter. Okay, after this point, before we start the design and we draw the moments, we can check the shear quickly. So after this point, we have shear check. Now step 5, yes, shear check. Okay, to calculate the shear check, what do we have here? Shear check, we need to calculate the VD. We already calculated it. We want to compare the VD with the VCR, V critical. Okay, So if the VCR was bigger than the VD, so no need for shear reinforcement. How to calculate the VCR? As we see the formula here, VCR equals to 0.65 times FCTD times BW times D. Okay, BW is always 1 meter. D, we will calculate D here on the side of the page. So D will equal to the HF minus CC minus the phi divided by 2. Okay, HF it equals to 13 in this example. HF was 13 centimeters. So we will calculate it in millimeters. So we will write 130 millimeter minus the clear cover. CC is the clear cover. In general, clear cover we take it as 15, 20 depending on the question. So I will take it as 15 millimeter, which is 1.5 centimeters. And here the phi, the thickness of the bar or the bar size, I will consider it as 10. In general, usually we use it as 10, so 10 divided by 2. So 130 minus 15 minus 10 divided by 2. Okay, and it equals 110. 110. Okay, another point. What's the meaning of this? The D is the effective depth. So when we are designing, so let's consider that this is the original reinforcement that we have it. So D it equals from the middle of the support of the bar up to the top of the slab. This is the D and this is the HF. So we have this space, or this space from here to here, it's the clear cover, and this is from the surface of the steel bars, and from the middle of the steel bar up to here we will calculate half of the steel bar. And this is how we calculate the D, because the D is from the middle of the steel bars up to the top. So that's why D is equals the HF, the whole total length, now minus the clear cover minus the half of the supports, half of the steel bars. After that, we got the VCR. Okay, no, we still also have the F. We didn't calculate the F yet. Okay, FCTD. In some books, we have as a constant value, but in this case we calculate it. So the formula is 0.35 times the gamma of concrete, which is 25, the unit weight of concrete, divided by 1.5. So F will equal to 0.35 times 25 divided by 1.5, 1.17. It equals 1.17 megapascal. So let's calculate the VCR. VCR will equal to VCR equals to 0.65 times 1.17. We just got it. BW is 1000 millimeter because we are designing for 1 meter. So BW is always 1000 millimeter. Because when we design, we take as like only a layer of 1 meter, and we design according to it, and we apply the design to the rest of the slab. And times the D was equal to 110. So the VCR equals 83,416.67 Newton. This value in Newton, we will convert it into kilonewton, which is divided by 1000 divided by 1000, and it equals 83.42 kilo in Newton. However, VCR is bigger than VD. VD was 19.36, so VCR is bigger than VD, and we are done with this point. Okay, after that, while we are done with the shear check, now we will draw the moment. We'll draw the moment before starting before starting the design. We need to draw the moment. So this is the shape for the moments. So all the values we got, first of all 11.71 are here. So here it's negative 11.71, right? 11.71 again, 11.71. After that we need to calculate okay, also we have here 4.73, 10.31, 8.48. So 4.73 here also negative, and 4.73 also here negative, and here we have 10.31 for both this one and this one, and here we have 8.48. Just a quick check for 84.4. Yes, exactly. These are the moment. According to this draw, we will start designing.